everybody, welcome to a new design mathematics video on ancient Mesopotamian mathematics. We finished up Africa and now we're kind of going into the Middle East. This is going to be over 2 days, so we're going to do two separate videos as well as some other reading and watching videos and that kind of thing. So just know that I'm going to continue this video later on. So ancient Mesopotamia, over here on the left we have Egypt and Africa. There's the Nile River. We have the Sinai Desert. So this green region is Mesopotamia, is the Middle East. It was called the Fertile Crescent. There was a lot of rivers. The Euphrates, the Tigris are some well-known rivers. But this is about where Iran, Iraq, Saudi Arabia, all those places are today. That's where the ancient Mesopotamians used to live. There may be some cities on this map that you might be familiar with, like Babylon. And then over here we have Canaan and Palestine. We have Syria. You hear a lot about Syria in the news. It's still around. And then, of course, you have ancient Egypt. You have Turkey over here. Greece is kind of on this far left side. So we've got lots of activity happening in this region because there are these really fertile rivers. And so civilizations grew there because it was easy to grow food. With the relative ease of food production, people settled down in one place instead of moving from place to place and being nomadic. And so populations grew and towns and cities were built and people started having more stable jobs and things like that. So it just kind of exploded as far as even technology in this region. So the first group, the earliest group that we know of, is the ancient Sumerians. The ancient Sumerians were in the southern region of Mesopotamia, so they were closer to the water from the, I guess it was one of the seas closer to the Indian Ocean. Some of the scholars argued that they may have been the first civilization in the world, dating back to 3500 BC. Sumer was the birthplace of writing, the wheel, agriculture, the arch, the plow, irrigation, many other innovations. And then we also have later on in the same region, we have the Babylonian civilization, and it dates back to about 2000 BC, created an empire out of territories from the former Akkadian Empire. And so you may know of Hammurabi's Code, have heard of that, or maybe even the Gardens of Babylon. So those are some well-known things about Babylon. The early writing system, prehistoric writings in the area, dated back as far as 3500 BC. Early cuneiform writing emerged about around 3000 BC. And the Sumerians developed a pictographic, kind of like the Egyptians have the hieroglyphic. So they came up with a pictographic system, and then it kind of morphed into something a little bit different. So it started off as pictures and then changed. They took almost like a stylus that was kind of wedge shaped, and they took it and they pushed the stylus into clay tablets to make these markings. And so we know about their knowledge of math more so than the early Egyptians' math because of what they left behind. So if you look here, in the red, these are what the words mean. These are in the blue are actually their words. So sag is head, and it looks like a person's head. And then about 200 years later, it looks like a head laying down. And then it kind of gets this weird kind of abstract shape to it, and then becomes just a series of lines and kind of triangles, where the triangles are like a wider piece because you have that wedge-shaped character. To walk, it kind of looks like a leg with a foot, and then later on it looks like that same thing, both laying down, kind of like the head, and then it turns into this kind of abstract piece, and then we get, where it's just completely, the image is gone. We have a hand, and it rotates. And then we get some other pieces. Barley looks like, a grain, and then a grain on its side, and then we pick up some of the other things. So you're hopefully able to kind of see the progression of how did it start and how did it come about being. So we're still dealing with hieroglyphics even in this 1000 BCE. We're still dealing with hieroglyphic type shapes, but you can kind of tell the earlier that they were, more so you could tell and be able to read it better than maybe the 1000 BCs, those symbols. Okay, so we know about their number system. Sumerians created a base 60 number system, and the Babylonians adopted that same number system later. 0 came much, much later. This is about place value, but place value in that there is no 0. You're going to have to deal with things in multiples of 60. So 1 and 60 look exactly the same. So then you would need 61 and 62. And so you end up with this place value idea. We're going to talk about that a little bit more in detail and give you some examples of it. Okay, so some historians have argued that the number 60 has many factors. That might be why base 60 was the thing, the number to choose for the number system. So what are the numbers that are factors of 60? What numbers multiply to give you 60? Well, 1 and 60. 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10. I think that's it. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 factors of 60. So 60 is a number that's easy to divide into many different types of amounts. And we see that 60, we actually have pulled that 60 into quite a few of our current systems that we use. Like there are 60 seconds in a minute, there are 60 minutes in an hour. How many degrees are in a circle? 360, which is a multiple of 60. So we use a lot of this base 60 numbering system. And one of the reasons why we think that the Sumerians and the Babylonians used it was because that you could divide it into those values. The systems of weights and measures in the Fertile Crescent relied upon fractional amounts like 1/3 and 2/3, which if you did 1/3 of 60, you get 20, and 2/3 of 60 is 40. So that would mean that dealing with calculating amounts of grain, for currency and that kind of stuff is easier than if you did base 10 or base anything else. All right, so there is going to be a video about counting to 60 on your fingers, so you can watch that next after this video. But others argue that there are about 360 days in a year, and that this would account for using 60. Others, again, they're dividing into 3 sections. You can count to 60 on your fingers, but nevertheless, Mesopotamian civilizations used base 60 in their counting system. So they used only 2 distinct cuneiform symbols. So you have like this little triangle on a stick, kind of looks like a popsicle. And then you have this other one that looks like this little triangle pointing the other way. I almost think of it like a little fishy. And so the rightmost column are the ones. So if you notice, let's look at 11. So in the rightmost column, it's the ones. If you compare this to the column before it, here's a 1, there's a 1. Here's 2, there's 2. Here's 3, there's 3. Here's 4, there's 4. And they start stacking stuff. Okay, 6, 6, 7, 7, 8, 8, 9, 9. And then for 20, they get 2 tenths. Okay, so the next column, once you've figured out how many of these you need, as the numbers get bigger, we're going to start getting more and more of these digits, these individual digits, multiplied by 60 to the first, or 60 squared, or 60 cubed. And so it's going to, you got to do a little bit of math to do these. So 1 and 60 are usually not too bad. It's the numbers that are a lot bigger where you have to do math and you might need a calculator of sorts to help you. And you can, if you see, you can even use different fonts. So this is a stack of 4, like 4 here. This is a stack of, is that 7 here, but this is also a stack of 4. This is a stack of 6. So it's almost like there's different fonts, different ways you can kind of write this. So we're going to read the numbers, and we're going to look at probably making sure we have a calculator of some kind, because we are going to have to raise to the power, raise 60 to a power, and then we're also going to have to add a lot of these values. So we're going to start on the left. We're going to start on the left. We're going to start on the right. So we're going to start here. And if you notice, there's actually, I'm going to try to do them in different colors. So the spacing, it's almost like you have 4 different values here. Okay. Here, there's 1 here, here. And then over here, you can kind of use your triangle guys, as guides, but it's almost like this one's got 5 different ones. They kind of have to be like really close together. Okay. So just kind of depends on who's writing it, I guess. All right, so we're going to start on the right, and we're going to identify. Now this one, these guys don't have any sticks. You could draw them, but this is 2. And then we're going to do times 60 to the 0. And then for this one, we have 1, you can put on a stick, 1 times 60 to the first. And we're going to be adding these together. And then for the green one, we've got, that's a 10. 10 times 60 squared. Plus something there. And then for the one all the way on the left, looks like we are in this boat right here. We've got 2 little triangles. We've got 4 of those things. So this is 24 times 60 to the third. All right. So, and this is the reason why you had people actually, like if they were going to, calculators right now are machine jobs. There were actual people that would sit around and figure this stuff out and got paid for it. All right, so 24 times 60 to the third, very large number, 5,184,000. And then we've got 10 times 60 squared is 36,000 plus 60 plus 2. So we're going to add all of these values together. Plus 60 plus 2. We get 5,220,062. And that's how you write that number in uniform writing. So this and this, they're the same number. Now, I like our number system a little bit better. There's less work to it, but that's just a personal preference. All right, let's look at the next one. Remember, we're starting all the way on the right. This one looks like the little fishies, and there's like a stack of 4 of them. So I think that is 40. So 40 times 60 to the 0. And then the next one, we've got another 40, but then there's 6. So that's 46 times 60 to the first. And then that's 57 times 60 squared. And then that's 1 times 60 cubed. Okay, so notice that you're kind of working backwards with your 60s, and you're going from a power of 0 up, in this case, to a power of 3. So 60 cubed is 216,000. And then I'm going to add to that 57 times 60 squared. 205,200 46 times 60 is 2,760 plus 40, and then we're just going to add them all together. So 216,000 plus 205,200 plus 2,760 plus 40 is 424,000. This number translates into that value. Alright, so let's do another one. Ooh, look, we start with a 40 again. So that's 40 times 60 to the 0. Which, let's just write that as 40. That's 40. And then to that we're going to add, that's 6. I'm going to go ahead and 6 times 60 is 360. And then that's 20. 20 times 60 squared is 72,000. We're going to call that 4. 4 times 60 cubed is a big number. 864,000. And then 40. That's 40. 40 times 60 to the 4th is a very, very large number. Okay, so that's what? 518,400,000. I don't know why those people would need to know that number, but maybe they're counting something. There's a lot. Alright, I'm just sticking it in the calculator. 336,400. So those two are the same number. So you have this idea of for each place you're multiplying by 60 raised to a power. And so, I mean, it can control large numbers. It can hold large numbers with a lot fewer symbols. But it's not easy to read unless you're working with the same numbers like repeatedly over and over and over again, and then you might just get an idea for what they are and not have to calculate them every single time, which is kind of what we do, right? We know what a 5 represents. We know what a 1 represents. When we were little, it may have taken us a little while longer to know what that represented. Alright, so that's reading them. Oh, look. Oh, we must have done that one wrong. Maybe we were looking at it. We should have looked at it like this and this and this. So let's look at that one again. So this was 40 times 60 to the 0. This would have been, again, the font's funny. So that would be 26 times 60 to the 1st. And this would have been 44 times 60 squared. 44 times 60 squared. That's probably more like it. It would be helpful if I could read my own problem, wouldn't it? Times 60 to the 1st. Yeah, this has got to be it. Plus 40. So 158,400 plus 156,0 plus 40. Oh, I mistyped something in my calculator. Yep, I get my 160,000 there. That's why I have it there, so I can remember. And I didn't remember and check it. So how you write them doesn't matter. I think we did better with the other ones that had giant spaces between them. Like there was a big space here, and a big space here, and a big space there, and definitely the one above. But this one, there was, you know, kind of, is there a space here? Is there a space here? I don't know. So how you write it is very, very important. All right, let's try to write with some cuneiform numbers. So we're going to have 3 different numbers. This is not like a really big number. This is 3 different numbers, 23, 158, or 185, and then 756. So what we're going to do is we are going to look at drawing with our little triangles on a stick and little fishies sideways pointing triangles, how to do 23. So 23 is actually already given to us. I just want to kind of play around with that idea of what it looks like. So something like that. And everybody's handwriting is a little bit different. That kind of goes back to the problem that we had before with reading the last one. Let's see. There we go. That looks a little bit better. And then 23, so I'm going to do 3 little triangles on sticks. There we go. There's 23. All right, 185 is something that doesn't fit on this table. So let's think of this as 180 plus 5. 180 is a multiple of 60. It's 3 60s. Okay, so what I need to do is I need to find 3, that would be here. That would be my 3 times 60 to the first, and then I need 5 of these, and they kind of get stacked, I think. Okay, so I definitely want to leave a space in between those so that people can read that. Hopefully that you'll be able to tell that they are separate. But get the 5 down and get the 3 times 60 to the first down. All right, so let's see. I know that I'm going to have to do something similar with that. So what I'm going to do is I'm going to take 756 and divide it by 60 and see what I'm left with. Looks like I'm at 12.6. So that would mean I need 12 times 60 to the first. That would be 720. And how far am I off from 720? 36. So I need to draw a 12 and then kind of leave a little bit of a space and then draw 36. So 12 is fishy guy, 2 triangles on sticks, and then leave a definite space and then do 3 of these and then 6. All right. So definitely have a space in between those. So I think dividing by 60 is a good idea. Take whatever number you have, divide it by 60. If it's in the thousands, like if it's beyond 3,600, which is our 60 squared, divide it by that, and then look at what you have left. If you can divide that answer by 60, then you can figure out what needs to be in the next decimal place value, and then look at whatever you have completely left over. The Sumerians developed a complex system of metrology, the science of measurement, in 4000 BC. So if you notice that they have different, this is the unit, and this is the ratio, and then this is the Sumerian word for it. So they have a grain, a finger, a foot, a cubit, a step, a reed, a rod, and a cord. So I would say the foot and the cubit are probably the ones that are best known. You may have heard of a rod, and then even a finger maybe. A nation's system of measurement does not necessarily reflect their measurement of their system of numerical notation. So just because they had a specific numerical notation doesn't necessarily mean that that was what everybody used in their day-to-day business dealings and things like that. So they actually used fractions. If you notice that we've got 360, 1/360th, 1/60th, 1/3, 1/2, 1, 3, 6, and 60 meters in their measurement. So these are just things that, you know, it's interesting to see a development of a metric system or a measurement system. They also came up with units of area. So they had a garden, a field, and an estate, a sar, an iku, and a bur. And so they had, again, these are things that are multiples of 6, at the very least, if not 60. So they had different dimensions there, and they turn into equivalents of meters. Time. We have a gesh, a watch, a day, a month, and a year. And so there's the Sumerian, the ratio. So a gesh is 1/360th, which kind of translates into 240 seconds. A watch is 1/12th, which is 7,200 seconds. A day is 1. Okay, so you're getting hopefully the idea. So 1 year was in Mesopotamia divided up into 360 days. 1 day was about 12 times 30, um, so 60 subunits. The base of the Sumerian time notation was not 60 but 360. Although the base of our time notation is 60, and we tend to say that we get it from Sumerians and Babylonians. Sumerians had 12 hours in a day, but at some point they changed it to 24. Clay tablets. So here are some, you can see the cuneiform, the wedge-shaped writing with your numbers. From 2600 BC onwards, the Sumerians wrote multiplication and reciprocal or division tables on clay tablets and dealt with geometric exercises in division. So they are creating tablets, tables of things to go back and refer to. There are many tables that have lists of squares, cubes, or square roots. The Sumerians are believed to be the first to find the area of a triangle and the volume of a cube. Later Babylonian tablets dating from 1800 to 1600 BC cover topics like fractions, algebra, methods for solving linear, quadratic, and even cubic equations, calculation of regular reciprocal pairs or pairs of numbers which multiply together to give 60, working with Pythagorean triples, which this is way before Pythagoras, so that's interesting. One Babylonian tablet gives the approximation of square root of 2, accurate to an astonishing 5 decimal places. Tables of compound interest, the estimation for pi being 3 1/8, which is 3.125, which is a reasonable approximation of 3.14159, blah, blah, blah. So it's pretty close. And there is a tablet called the Plimpton 322, which was discovered or recovered from an unknown place in the Iraqi desert. It was originally written around 1800 BC. The tablet lists Pythagorean triples written in Babylonian numbers and suggests that Babylonians may well have known the secret of right-angled triangles, that the square of the hypotenuse equals the sum of the square of the two other sides, many centuries before Pythagoras. So this is a list of triangle sides and that they fit with right triangles. So let's talk about Pythagorean triples. They are 3 positive integers. A squared plus b squared equals c squared will work for those. The most common triple is 3, 4, 5. So 3 squared plus 4 squared equals 5 squared. So if you remember a squared plus b squared equals c squared, this has to be the hypotenuse, c. And then the hypotenuse is the longest side. So that would mean that I could take 3 squared plus 4 squared, or do 4 squared plus 3 squared. And if this is true, 9 plus 16 is 25, which 9 plus 16 is 25. That means that 3, 4, 5, they are sides of a right triangle. So we don't have any decimals, we don't have any square roots, we have nice numbers. However, right triangles with non-integer sides do not form Pythagorean triples. So they could still work in a Pythagorean situation, but they're not Pythagorean triples because they are not nice whole numbers. So the triples listed on the Plimpton 322 are too many to have been constructed by brute force. So they couldn't have just sat around and just tried to figure out, well, do these numbers work? Well, do these numbers work? Do these numbers work? So from a modern perspective, a method for constructing such triples is a significant early achievement, even before the Greeks knew about it. All right, so Find 2 additional primitive Pythagorean triples other than 3, 4, 5, and 5, 12, 13. So we need to find some more. So let's see if we can figure out a pattern. So we can tell that we've got these differences between these values. And if you take the 2 numbers that are next to each other and subtract the biggest number minus the smallest number, and you get a squared number, then you have found a Pythagorean triple. So here 12 and 13 work because when I subtract those 2 values, I get 25, and 25 is a squared number. So if we go into further numbers, so 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so I'm going to look at squaring some things. I'm just going to stick them in the calculator and square them. I'm looking for when I take a difference, ones that are a squared number apart. So 16 squared is 256. The difference there, 31. So not those guys. 17 squared, 289. Minus 256 is 33. Nope. But I should be coming close to, well, no, I'm only counting odds. 36 would be another squared number, but I'm not going to be able to reach that because these look only odd. So the next odd number that is squared is 49. So we've got a ways to go. So this would be 35. This would be 37 if you're following the pattern. This would be 39. The difference between 20 and 21 would be 41. Then 43, and 45, 47. Has to be somewhere in here, 49. So let's see. 23 squared, because I think I've gotten off of my numbering. 529, 24 squared, 576. So 576 minus 529 is 47. So there's where my 47 goes. So that would mean the next one. So 25 squared is 625 minus 576 is 49. 49 we know is 7 squared. So 7 squared plus 24 squared equals 25 squared. So let's try it out. I already know that this is 625. 7 squared is 49. 49 plus 576 equals 625, so that is another Pythagorean triple. So you're looking for when you subtract the 2 values that you have squared, you get a number that is a square. But notice that we're following this pattern of odd values being squared. So then the next one, we couldn't find an 8 squared in there. We would have to find a 9 squared. So we would need to find which numbers are 81 apart. Interesting. So you could sit around and try to figure out these patterns and generate these Pythagorean triples, which is what they were looking at. They were looking at patterns. They were not looking at trying to figure out, does 21 squared plus 22 squared, is that, going to work out? That's not what they were looking at. But you will notice that in your Pythagorean triples, you will have 2 numbers that are back to back. 2 numbers that are back to back. All right, so your job, here's 7, 24, 25, here's 9, 40, and 41. That's the one with the 81 piece that we were talking about, because 9 squared is 81. There's 5, 12, 13, 3, 4, 5. Find 2 additional primitive triples. So we found 2. I found 2 that create a right triangle. And there's more. It just keeps going on and on. The next one would be one with a side of 11. And so you'd have to figure out where the difference between the two values right next to each other is 121. Now, some people will say, well, I can multiply each of these sides by 2, so I can get 6, 8, and 10. That is not a true Pythagorean triple because those are variations of ones that are the base Pythagorean triple. So you could technically multiply them by 2 and create a different Pythagorean triple, but it's not quite the same. It does go kind of like simplifying a fraction. You do want to go as simply as possible. All right, so that's where we're going to stop this video, and then you're going to pick up for the second part of the assignment, watching some other videos and watching me wrap this up. All right, I'll see you in the next video.